How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, again, still. And my principal business is
chemistry.
Stereoisomerism is the science of studying different spatial arrangements of atoms. You know when you look into the mirror and see that beautiful reflection? Take that mirror image effect and apply it to a chemical compound. Stereoisomers are fascinating in pharmaceuticals because a compound might transform from pain-relieving naproxen to a lethal drug. By using prefixes D- or L- in the monosaccharide's name, scientists can identify one of two possible forms and therefore theoretically identify the life-saving naproxen from its counter-harmful stereoisomer. This is necessary as stereoisomers have the same molecular formula and bonding. Cis and trans are a predominant subclass of stereoisomers. When saying cis, scientists mean on the same side. When saying trans, they mean across. As seen by the diagrams of cis-2-butene and trans-2-butene, the methyl groups have rotated around the double-bonded carbons or become across from one another, giving them the prefix trans. You might remember from biology that all trans molecules are man-made. The most common example is margarine, a dehydrogenated trans fat. Now let's say you were given atom butane, chemical formula C4H10. This 4-carbon structure could be drawn in a few ways. The two middle carbons could overlay to form the following structure. The arrangement where the methyl groups are opposite to each other is identified as a staggered start or conformation. However, this is not the only arrangement that butane can exist. Consider a butane molecule where instead of an opposite methyl arrangement, methyls are placed closer together. This results in an interaction between the methyl groups called a steric strain. When this rotation around the bond is shifted by 60 degrees, you get what is called an eclipse formation. This is similar to an eclipse formed by an overlay of the sun and moon. Proximity between the methyl and hydrogen atoms causes torsional strain. This strain makes the eclipse conformation unstable in comparison to the staggered start. However, this is not the most unstable form. The most unstable form is rotated in a way that places the methyl groups in close proximity. This form has the most energy of the three formations because it has both torsional strain and steric strain. This means that the staggered start is the most stable. An interesting addition is seen when the rotation in correlation to the energy level is graphed. The maximas in the graph would be eclipse formation, with the minimas being staggered conformations. This means that eclipses have higher energy, meaning higher activity and lower stability. The opposite is true for staggered conformations. Newman predictions in the scientific term are used to classify molecular diagrams which show an atom from front to back. You might recognize this diagram as we have been using it this entire video. The same diagram can be drawn in the form of a Sawhorse representation. This is the same compound drawn from an oblique angle. These diagrams can be easily rotated to show different conformational isomers. The definition of cycloalkanes is easily found in the name, with cyclo referring to a continual cycle and alkane referring to single-bonded carbons. Hence, cycloalkanes are just cycles of single-bonded carbons. When naming cycloalkanes, identify the number of carbons and add the prefix cyclo to the alkane's name. For example, you can have cyclopropane, cyclobutane, or cyclopentane. A quick and common example is a cyclopentane with additional subgroups. In this case, we would first number the carbons, identify the additional groups, and then add it chronologically with the parent function on the end. Cycloalkanes also vary in energy and stability. It is not fair, however, to compare the overall energy, as of course the addition of CH2 molecules will result in an overall increase of energy. We must therefore compare individual cycloalkane strength as a rate according to the number of CH2 groups. If we look at this rate instead, a 6-embered ring would actually have less energy than the 3-embered ring, and therefore more stability. Hence, you get a pattern that looks a lot like this. Due to the higher energy per CH2 bond, the stress on cyclopropane is severe. There are many ways it can alleviate the stress. The first way is by making the bond orbitals bend outward. It is stuck in an eclipse formation with no possible way of achieving a staggered formation. It can undergo something called a ring opening reaction in order to relieve this torsional tension. The cyclopropane, when combined with the hydrogen molecules, forms cyclopropane to propane. A fun fact about cyclopropane is that due to its blood solubility, it was often used as an inhalation anesthetic until the 1960s. It did not induce vomiting or cause liver damage like previously used anesthetics. However, due to its instability, even a static spark could trigger an explosion with disastrous consequences for the patient. Cyclohexane can adopt many formations. The most common is the boat and chair conformations. The most significant difference between the two is seen when comparing torsional strain. The boat conformation experiences a surplus of steric interactions called flagpole interactions, making it less stable than the chair conformation. The boat can alleviate some of the strain by forming a twist boat conformation. This chair can also exist as what is denoted as a half chair. There are many conformations in which cyclohexane can exist. However, when graphed, according to stability, chair is the most stable and therefore the most common. Additional groups on a cyclohexane can be located either on the axial or equatorial regions of the cyclohexane. When an axial molecule is replaced with an element other than hydrogen, there are steric interactions that occur. This is not preferred due to the instability that occurs. These interactions are also known as 1,3 diaxial interactions, where the numbers 1 and 3 describe the distance between the substituent and each of the H's. For this reason, cyclohexanes with an equatorial substituent are usually preferred. A chair conformation with equatorial positions requires less energy and is therefore more stable. However, when you have a chair conformation with one axial and one equatorial substituent, one must see which group exhibits a greater preference for being equatorial. In this example, the energy cost for axial ethyl to become equatorial is 8 kJ per mole, while the energy cost of an axial chlorine is 2 kJ per mole. Therefore, since it takes less energy for chlorine to move to the equatorial position, it is more likely to be in equatorial position as this is more stable. Cis and trans stereoisomers can be drawn in chair conformations as well. Cis molecules has one in the equatorial position and one in the axial position, whereas trans would have either 2 in the axial positions or 2 equatorial positions. Trans is more stable because it can adopt a chair conformation with 2 equatorial positions. Let's recap what we learned today. We started with labeling stereoisomers via their prefixes. We then continued by learning about cis and trans molecules. We then examined different conformations, specifically the Staggered and Eclipse conformations. We then looked at how to draw these conformations via Newman and Sawhorse projection. We finished it off with cycloalkanes and all their complexities. Thanks for watching, and hopefully this video is good enough for Canada.